Ohayou gozaimasu. I've been working on Cassandra for 5 years now. Who has used Cassandra in the audience? Very good. Who is just interested in learning about Cassandra? Okay, very good. So my talk today will be a little bit more oriented towards people who are already using Cassandra, but hopefully for those of you who are new to Cassandra, I hope that you will take away some interesting knowledge from this as well. For the 5 years, for the first 4 years, rather, that I've been working on Cassandra, we were primarily concerned with 3 core values: availability, scalability, and performance. This past year, in 2013, we focused on a new core value, on ease of use. So one of the primary ways that we focus on ease of use was by adding the Cassandra query language. So on this page, on the left, all of the statements here are valid in both SQL and in CQL, in Cassandra as well as in relational databases. So create table, create index, select from where, all of these are valid in the Cassandra query language. As part of this, we've also added native drivers for languages to build applications using CQL. So the Java driver and the .NET driver are both generally available, with more in beta. We're also working on drivers for languages like PHP and Ruby as well. DataStax also created a free tool called DevCenter, which allows you to graphically interact with and explore your Cassandra databases, as well as helping you write queries with query completion for your table names, your column names, and so forth. This is the first tool of its kind for a NoSQL database. An important feature of the Cassandra query language is the ability to see what goes on in your cluster when you execute a query. So here's an example of tracing a simple insert statement. You can see at the top in blue, these first lines are logged by what we call the coordinator node. So this is the node that the client connected to and gave the query to it. Then the next lines in green, the coordinator forwards that query to the machine, to the replica that actually needs to store the row being inserted. And then the replica acknowledges back to the coordinator, again in blue. So because Cassandra is a distributed system, pulling these records together across multiple machines is important to understanding how the cluster works. And so in a CQL shell, turning on tracing, all you have to do is say tracing on, and then you will get this inspection into your query activity. We also added, at the beginning of the year, we added support for authentication and authorization to Cassandra. So to enable this, to enable authentication, you go into your cassandra.yaml and you set the authenticator class in your configuration file. By default, Cassandra ships with the password authenticator, which stores users and passwords locally in a Cassandra system table. DataStax Enterprise, which is our commercial distribution of Cassandra, also offers a Kerberos authenticator, which integrates with enterprise single sign-on systems. So once you've enabled this, you can create users, you can set their passwords, and so forth. Now, it's important to note that the default super user in the authenticator is username Cassandra, password Cassandra. So this allows you to bootstrap your authentication, but what you should do is you should create a new super user and either alter password, or change the password of the old one, or drop it. That will let your cluster be secure rather than having the default super user still present. Cassandra also supports authorization now, which is closely related to authentication. Authentication says what users exist and how do I know that you are the user you say you are. And authorization is once you've logged in, what privileges do you have in the cluster. So we split it up into select and modify privileges, and that's at a table as well as at a key space granularity. If I grant all on all key spaces to a user, then that user will be able to access all the tables in all those key spaces. So it's hierarchical. So everything I've covered so far was introduced in Cassandra 1.2, which was released almost exactly a year ago. In September, we released Cassandra 2.0, which made a number of important improvements. The first of these is lightweight transactions. So the motivating feature for lightweight transactions is that sometimes I need to establish a linear order of operations. In particular, I need to establish an order of modifications being made to the database. So normally with Cassandra inserts and updates, there is no way to lock rows. And sometimes I need to do that. For instance, if I am creating users for my application and I want to allow users to request a specific account name. And the naive way that I would do this is I would say, select name from users where username is Patrick McFadden, for instance. So if I have two users trying to create the same account at nearly the same time, then Cassandra will tell the first, this row does not exist. There are 0 rows matching P. McFadden. Meanwhile, the second user performs the same query and asks, does this user exist? Cassandra says, no, it does not. The first one says, okay, well, let's create the user. And the second one says, I want to create the user as well. So this one, the second one, actually overwrites what happened with the first. So because there was no locking, I was able to basically introduce a bug into my application. So Cassandra's approach to solving this problem then is something we call lightweight transactions. We don't want to use traditional locking because introducing locking into a distributed system causes many problems. For instance, if this client says, I want to lock the P. McFadden row, and then the client dies before it unlocks the row, now that row will be locked forever. Or I have to introduce some kind of process to go through and break obsolete locks. So we don't want to introduce locking per se. Instead, we combine the checking, the select, and the insert into a single operation. So this is what that looks like. I have my insert into users, column names, values, So far this is exactly the same, whoops, so far this is exactly the same as the insert here. But then I add one more clause to the request, if not exists. So that turns this into a lightweight transaction that will only perform the insert if the row does not yet exist. And it performs this in a concurrency safe manner with other clients. So if my second user comes in and says, okay, I want to do the same thing, I want to also create this user if not exists, for one of those, Cassandra will return a result set that says it was applied. So that I'll have a single column there called applied, and it has the value of true. For the other one, it will say applied is false, so somebody else created that row first, and to give you extra information to decide what to do next, I'll tell you what that row was, the values of that row that got inserted before yours. So this is allowed for updates as well as for inserts. So I could say update users, set some values if created date equals such and such, for instance. So I can apply this to perform this update based on this value, not just for inserts. This is done using the Paxos consensus protocol, which has a number of important characteristics for a Cassandra system. Notably, Paxos is a quorum-based protocol, which means that as long as a majority of the nodes in my cluster are up, then I can make progress. I can perform lightweight transactions. There is no need for a failover or a master node that can impede availability. So it's a very good fit for Cassandra where every feature needs to be highly available. It's similar in principle to two-phase commit, but one of the important differences is that when there is an unfinished or an in-progress operation, then replicas will inform any new leader of those operations so that they can be completed without the problems that happen in two-phase commit when the master dies. There's a very readable paper about Paxos called Paxos Made Simple. So if you want to go into more detail on that, I would highly recommend that. Some of the other properties of Paxos for us, a big one is that it does require more round trips between the coordinator and the replicas. This is very important because that has a big impact on the performance of these operations. So what this is saying is that I should only use lightweight transactions when I absolutely need the linearizability that it provides my application. Now there's some other features of our implementation. For instance, if you're familiar with consistency level 1, consistency level quorum, we've introduced a new consistency level called consistency level.serial. What this does is it allows you to perform a read operation, a select, that is also linearizable with the lightweight transactions in progress. So you would not need to do this with your inserts because your lightweight transactions are automatically performed at basically the serial consistency level. But this is to allow you to have your selects opt in to the linearizable transaction machinery. We also have a blog post up. I'll have this URL available. I'll send the slides out to the organizers with more details on our implementation. As I said, you only want to use this for a small part of your application because of the performance implications. For more information on how to build applications without transactions, I recommend a talk given at the San Francisco Cassandra Summit by a man named Christos from Netflix. He called it "Eventual Consistency is Not Hopeful Consistency," and it's an excellent talk on that subject. Another feature we added to Cassandra 2.0 is cursors for CQL drivers. So what this does is, if I have a table full of data and I want to page through, I want to scan through that table and do something with all of the rows in that table, what I would have to do in earlier versions is something like this. I need to write a select statement, and then I need to pull out, for instance, 1,000 rows at a time. So after I get my first 1,000 rows, I'll say, give me the next rows where it's either a new partition or it's in the same partition, but so this row is this line is new partition, or it's the same partition but a more recent tweet ID. And I'll need one of these clauses for each column in my primary key. And since Cassandra encourages using natural keys, this can become painful as an application developer. It's not, the performance is fine, it's just a lot of boilerplate to write for that kind of query. So in Cassandra 2.0, all you need to do is write this, and the cursor takes care of fetching additional rows as you consume the first ones. An interesting thing about this is actually fault tolerant across the cluster. If the coordinator that I'm talking to fails, I can reconnect to a different coordinator with the same cursor object and pick up where I left off. So the state of the cursor is embedded client side so that it can fail over gracefully. We've made some other minor improvements to CQL in 2.0. One of those is we've introduced preliminary support for select distinct. In particular, you can now write select distinct and then the partition key from a given table. So in this table, user ID, the first column in the primary key is my partition key. So I could say select distinct user ID from timeline. And that's very efficient in Cassandra because the partition keys are stored in a separate file called the partition key index, so I can give you distinct partition keys very performantly. No other forms of select distinct are supported because I would have to do a sort and merge at runtime to provide those. So this is the query we can support performantly, so that's what we've given users so far. Another is create table if not exists. So just support for scripting your application schema creation. It's just a little bit more convenient. Select as, for instance, I could say select date of created at as creation date. So it allows me to give an alias to those function call results. Alter table drop column. So up until now, once you've created a table, if you don't want to use a column anymore, you could stop using it and it would just be null, but you couldn't actually drop it. So 2.0 allows you to drop that column, and then when Cassandra goes through and compacts the data files involved, the disk space will be reclaimed that those values we're using. One of the features that we focused on more on the administrative side of Cassandra is optimizing our use of memory. So since Cassandra is a Java-based system, we distinguish between memory allocated on heap inside the Java virtual machine and off heap native memory. Typical JVMs can support up to about 8 gigabytes of heap memory before garbage collection starts to become problematic. But modern servers have much more than 8 gigabytes of memory available. So we want to move Cassandra's internal indexes of your data, we want to move those from the heap into native memory. So this was one of our focuses for 2.0. To explain exactly what we did, I'm going to walk through what happens when you read from a Cassandra data file, which are called SS tables. So the first thing we'll do is we'll check the SS table Bloom filter, which is a probabilistic set of the partition keys. So if we check that, if we check, for instance, our user ID partition key, and the Bloom filter says, nope, I don't have any Patrick McFadden's in this Bloom filter, then we're done. We don't need to go further because we know it does not exist in this data file. But if the Bloom filter says it's probably there, then we'll go ahead and check the partition key cache. So recently accessed partition keys will be cached in memory, and then we have a choice based on whether we find the key in the cache. If we do, if it is in the cache, we will skip this next part. We will go to the end of our process. So what I'm going to describe here is what happens if it's not in the cache. On a cache miss, we will check a summary of that partition key index that I mentioned. And we will use that, the binary search of the summary, to locate the approximate location of that partition key on disk. So I've got a line through the page here. Above the line is stored in memory, below the line is stored on disk. So this would be my first time that I would potentially touch the disk on this query, is in the partition index lookup. Once I've located that partition location, I will map that to the appropriate compressed location. So this stores uncompressed locations, and so I'm going to map that to the compressed block. Compression is optional in Cassandra, but it is on by default because it allows you to get that much more value out of your operating system page cache. So compression is almost always a performance win for Cassandra, so it's on by default. Once we know the compressed block location, we can go and fetch that again from disk. So of all of these structures here, the Bloom filter, the compression offsets, and the partition summary are all kept in memory, and they all grow linearly with the amount of data that you have. So this established a fairly low boundary on the amount of data that you could support per Cassandra node before Cassandra 2.0. Before Cassandra 2.0, you were looking at a maximum of about 1 terabyte of data per Cassandra node. Now that we have moved these three off heap, we estimate that we can support 10 terabytes per node, because these structures are now in the native memory where there are much less stringent constraints on our memory size. Now, it's worth pointing out the partition key cache is still on heap. It is not in native memory yet. But this has a constant size. It does not grow corresponding with the size of your data set. So we're less concerned with that. We're okay with leaving that on heap for now. Now, if you've run a Cassandra cluster in production, you know that one of the concerns is compaction, which is the process whereby we combine these SS table data files into new ones to be able to reclaim space used by obsolete data. So there are two compaction strategies that we have. Leveled compaction, that's what LCS stands for, leveled compaction strategy, and size-tiered compaction. Both of these have become single pass in Cassandra 2.0. So in earlier Cassandra releases, we would perform a single pass compaction up to about 64 megabytes of data in a partition, because we would have to read that partition into memory to compact it. If it did not fit in memory, we would do a two-pass compaction of that partition. So we've fixed that so that we can always do compaction in a single pass, no matter how large it is, without having to read it into memory. So this becomes much gentler on the garbage collection subsystem, as well as more performant, because I'm doing less disk I/O. I only have to read each partition once. This may be a little bit more cryptic as to what that means, so let me explain. Leveled compaction means that we will split our data files up into a series of levels. So we have level 1, level 2, level 3, and so forth. This diagram is not to scale, because each level is actually 10 times larger than the previous. So level 1, in reality, level 1 has about 10 data files, level 2 has 100, level 3 has 1,000, and so forth. And within each level, we guarantee that a given partition may only be present once. So if I go ahead and I say select star from timeline where user ID equals X, I'm going to guarantee that user ID X will be at most in one data file per level. So this gives me an upper bound on how bad my performance can get, how many seeks I will have to perform on disk. Level 0, however, is a special case. Notice that I have 4 files in level 0 and they are all orange. That's because level 0 is where newly flushed memtables live. They have not yet been incorporated into the sorted levels. And so I have to check each of those when I'm reading from any partition. The problem then is it's actually fairly easy to write data files faster than compaction can move them into the appropriate levels. So you get a situation like this where I have several hundred files in level 0, and I have to check each of those on a read. So my read performance starts to get worse, which means that I'm doing more reads from disk for each select, which means that I have even less I/O available to perform compaction and clear out level 0. So it turns into a vicious cycle where compaction is behind, so reads get slower, so compaction gets farther behind, and it can be difficult to escape from this. So what we do now in 2.0 is we'll actually perform size-tiered compaction, in level 0 until, to keep reads relatively fast until we can incorporate that data into appropriate leveled SS tables. So in the general case, this does not make compaction faster because I'm actually doing extra work. I'm compacting these files multiple times now. First, I'm compacting them while they're in level 0, and then I'm going to compact them again once I catch up. But what this does is it keeps the read performance from deteriorating when leveled compaction falls behind. So that's the win. It's not that leveled compaction magically gets faster because of this, but that read performance doesn't deteriorate under the worst case scenarios. I want to talk about reads from a higher level perspective now. So I talked about what happens when I'm doing a read from a single data file. Let's go back up to a higher level now and look at what happens from a cluster perspective when I'm doing a read. So I have a client on the left, and it's talking to some Cassandra node, the coordinator, and that coordinator will then relay that query to a node that has the data, and then the replica will send it back to the coordinator, and the coordinator back to the client. So nice and simple, but what happens if the replica fails during this process? Well, the coordinator asks the replica for the data, and then it dies, and the coordinator has to tell the client, sorry, I didn't hear back from the replica, so maybe he died, maybe he's so busy doing compaction he couldn't answer. I don't know what happened, all I know is it didn't answer. So in 2.0 we introduced something called rapid read protection. So what this means is that if I have this scenario where the replica dies before responding, then the coordinator will retry that request to a different replica. And then that will let me have a successful query instead of timing out. This is how it's supposed to work from a theoretical standpoint. Here's a graph of how that looks in practice. We have a 4-node Cassandra cluster here, and at about halfway through the stress test, we killed one of them. So the blue line here that goes, where the performance goes all the way to 0, that is with rapid read protection turned off. So it's equivalent to what Cassandra used to do in versions 1.2 and earlier. These other lines at the top here are different degrees of rapid read protection. I'll show you what those are in just a second, but you can tune how aggressive it is at performing these redundant reads. And you notice there is still an impact on the performance when I kill the node, because I have to retry all those queries to a different replica all at once. But the impact is much smaller than going all the way to 0 temporarily. So this is the different settings we have for rapid read protection from that experiment. So you can see with the rapid retry, which is the configuration setting, is called speculative retry. With that set to none, I'm pushing 39,000 reads per second on average, but with an average latency of 0.8 milliseconds. But the 99.9th percentile latency is almost 50 milliseconds. So one of the other effects of rapid read protection is it can reduce that worst case latency. So in the upper right, with retrying queries at the 90th percentile setting, which means that I will retry, I will do an extra read for the slowest 10% of queries. Notice that my latency for the 99.9th percentile comes down to 14 instead of 48. So the lower I set this, the more aggressive it will perform redundant reads. So if I set it down to 75th percentile, that means I'm doing an extra read on 25% of my queries now. And notice there's something interesting here. The latency is actually a little bit higher. Now, so normally I would expect this the more extra reads I'm doing, the lower the worst case latency will get. But here it's actually gone back up a little bit. The reason is, look at the throughput. So I've gone from 39,000 operations per second to 38,000, down to 36,000. So I've actually reached my throughput ceiling for this cluster. So I'm doing so many extra reads now that it's starting to eat in to my ability to fulfill as many requests as are being requested, and that's why the performance is getting worse again. So again, here I've set it to always do an extra read. So for each request, right out of the gate, I'm going to do 2 requests now instead of a single one. And you can see that the throughput has come down even further, and the latency has gone back up. The worst case latency has gone back up to 36 milliseconds. So it's almost as bad as it was to start with. So the default is to use 99th percentile, which is actually what we have here, 99th percentile, which means that I'm only doing extra reads on 1%, the slowest 1% of my queries, which is a pretty good balance between keeping my performance high and giving me that protection against a machine dying. So, we're working on Cassandra 2.1 now. I want to give you a quick idea of some of the important things that we're working on for that. One of the big features in 2.1 is user-defined types. So we introduced collections, maps, lists, and sets back in Cassandra 1.2. So that's been around for a while now. But you could not nest collections, which is to say you could not have a map containing lists or lists containing sets. So you could only have a single level of that collection container. So user-defined types allow you to nest collections as well as other fields. So for instance, I could create a type called address that has 3 primitive fields and then a phone numbers set. And then I can use that address type in my users table as a map value. So then I can go and I can select pieces of those types by using this dot notation. So addresses.city or addresses.phones, and those will come back in your result set. The next big feature for CQL in 2.1 is also related to collections. We've added the ability to create indexes on collections. So if I have a table of songs that has a tags column that is a set of text, I can create an index on that column and then say select star where tags contains, so that's a new keyword, tags contains blues. And that will give me back my result set. We've also continued to work on improving memory efficiency. So recall back where I was discussing the things that we've moved into native memory, that the first thing I check when I'm reading from a data file is a Bloom filter. So Bloom filters actually pose us a problem when I'm doing compaction. If I have two data files and I'm going to compact those, I don't know what size to make the Bloom filter. Bloom filters are tricky because you can't easily grow them. Unlike a list or a set, you can't grow them past their initial capacity. So I need to know how big to make the Bloom filter before I start compacting. It may be that these data files overlap a lot, and so I will end up with a data file that's roughly the same as one of the two that went into it, and so my Bloom filter should be this size. Or it could also be that these SS tables overlap not at all, in which case I need a Bloom filter that's as large as the two put together. The problem is that I don't know which of these it is until I'm actually already done with the compaction. So I can easily, so what Cassandra does is it will assume the worst case scenario. It will allocate enough memory for a Bloom filter where the two SS tables didn't overlap at all. But that means that if they did overlap, then I've wasted some memory. Morishita-san, who's talking later today about CQL, introduced functionality that uses a cardinality estimation tool called hyperloglog. And what that does is it lets me know how much these SS tables overlap so that I can always create the Bloom filter at the right size and not waste memory. Now we can also do some interesting things with cardinality estimation in compaction. So normally when I'm doing size-tiered compaction, or rather today when I'm doing size-tiered compaction, I just grab SS tables that are similar in size. If I have a tool that lets me tell how much these SS tables overlap, that would let me compact SS tables in a smarter way. And I can compact them based on how much they overlap rather than based on their size, which is a very poor proxy for guessing how much they overlap. So we would actually probably not use hyperloglog for this. We would probably use a different cardinality estimation algorithm, such as minhash, because hyperloglog actually requires a relatively large amount of memory. So we don't want to keep that resident in the Cassandra process at all times. So if we had a smaller estimate like minhash would give us, then we could keep that resident and use that at compaction time to determine the appropriate files to compact. The next thing that we've done for, so let me clarify one thing. This is me waving my hands a little bit. So the Bloom filter memory improvements, this is completed for 2.1. This part is probably going to happen for 3.0. It will probably not actually be in 2.1. That's still a work in progress. This next part, though, this actually is in 2.1 as well, improving the efficiency of repair. So when I go to repair different replicas of a table in Cassandra, I build what we call a Merkle tree, a hash tree. This lets me be very network efficient. So it's like rsync for databases. All the replicas do is they scan their data, they build the hash tree, And then the replicas compare hash trees. So if I start at the top, if I start at the root of the tree and those root nodes match, then I'm done. I don't need to transfer any more data, because if the tree matches, then I know the actual data matches too. If the root doesn't match, then I will compare the left subtree and the right subtree, and I'll be able to drill down quickly to find out which rows are actually inconsistent and just transfer those. So it's very network efficient. Repair is very network efficient. But it is not disk I/O efficient, because I have to scan all my data to build this tree. If I add new data, then the next time I repair, I have to scan all the data again, the new data and the old data. So what we have done for 2.1 is we have made it so that I only have to scan the new data that hasn't been repaired yet. Once I've repaired some rows in the table, I won't need to repair those again until they're updated again. Finally, we've been making some progress on performance in 2.1, and in particular, we've been working on reducing the memory used by the mem tables during writes. So this indirectly makes our performance better by making us have to flush less, and in turn having to do less compactions. So we're planning to, at the finish of 2.1, we should have reduced the memory by about 85% in the mem table, and so far that has resulted in about 50% better write performance, and that may go up further a little bit. So right now we're almost to doing our first beta for 2.1. We plan our first beta next week. It may actually be the week after, but very soon. Then we're planning a beta 2 in February and a final release by the end of March. I have a few minutes for questions if I can help answer any at this point.